Hello, we will now talk about Chapter 11, Section 2, which deals with a two-sample t-test for the difference in means, or a two-sample t-test for the true differences, they'll call it sometimes. So this is really similar stuff that we had in actually Chapter 9 when we did hypothesis testing with proportions, and then combined with Chapter 10, the stuff with means. So it's kind of a combination of those two things. Much of this you had before, but we kind of have some tweaks here. So let's read this problem. It says an administrator at a school wishes to see if there is a difference. There's a difference in the attitudes of the female students and the attitudes of the male students about the quality of the faculty at the school. The attitudes are measured by a test the administrator gives. She takes an SRS, a simple random sample of 50 of the female students. The females are given the attitude test and get a score of 78.2 and a standard deviation of 5.2. She also got a simple random sample of 45 of the male students who get a mean score of 74.6, standard deviation 8.2. Do the data provide evidence of a difference in the means of the population? Now, so the first thing we really possibly should notice is the fact that we're dealing with means here. Okay, we're dealing with means, and that means we're going to do a T procedure. And so when we're doing a test, the premise is what's going on is we want to see if there's evidence that the population means are different. The mu for the females is different from the mean from the males. Now, this is the sample mean. That is an X bar. So this is X bar for the females, okay? And so it is that. And the X bar, the sample mean for the males is that. And they are certainly different. We would expect them to be different because of sampling variability. But are they so different that it's beyond what we would expect just due to sampling variability, just due to random chance? That is the premise of what we're doing here. And of course, the standard deviations and the sample sizes we're going to use in our formula. We're asked to perform a test. Remember, anytime you're asked to perform a test, you have to do the THAME acronym. THAME. You got to do 5 things. You got to state the type of inference. You got to state your hypotheses. You got to check your assumptions or check your conditions. You have to do your mechanics, means come up with your test statistic p-value. And then you got to do your ending, state your conclusion. So you've got to become, of course, we've been doing this for a while now. So the first thing is the type of inference. And this has a bit of a complicated name. I'll do a 2-sample t-test for the difference in means. Okay, so that is the name of what we're doing that you have to memorize. Okay, and then your hypotheses. So now your null hypothesis in this section is always going to be the 2 population means, the 2 mu's are the same. Okay, never put the X bars in your hypotheses. It's always the mu's. We already know the X bars are different, so there's no point in hypothesizing about them. But it's the mu's that we want to see. So, and you define what your mu's are. Is that X bar sub F is the mean score on the attitude test for all the female students at the school. And mu sub M is the mean score for all the males at the school. So that is the way this should look. And so the null is that they're equal. The alternative is this could either be not equal to, less than, or greater than. Nowhere up here does it say we suspect less than or greater than. Okay, so you have to go with not equal to there. And it's not considered ethical to look at the sample values and say, oh, the females is more than the males, so we'll go greater than there. You can't do that, okay? So this is what we call a 2-sided test. By the way, the other way you'll see this written frequently is you'll see sometimes the null hypothesis is that mu sub F minus mu sub M is equal to 0, just subtracting both sides of the equation, mu sub M from both sides of the equation. And thus the alternative would be that mu sub F minus mu sub M is not equal to 0. So that's the other way of writing these hypotheses. Okay, so that's your type, that's your hypotheses. Now your assumptions, verify, and we've been doing this for like 4 chapters now, is that we sin, but since it is a 2-sample deal, we I-sin. We have to have independent simple random samples or independent random samples. We have to have independence. Our sample sizes can't be more than 10% of our population sizes, right? And then we have normality, okay? So we have to, so those 3 things. So let's do it. So the first thing, it says SRSs, there was 2 of them, so say plural, we're taking, so independent random conditions met. So, and then for our sample sizes to be less than 10% of the population sizes, what you do is you just take your sample sizes and multiply them by 10. The 50 and the and the 45, multiply them by 10, and you say, well, there has to be at least 500 female students and 450 male students at the school for our little n's to be less than or equal to 0.1 times our big N's. Sample sizes and population sizes, okay? This ensures that we can use the formula for standard error, and that's asked about a lot, okay? So make sure you're cool with that. All right, and so lastly, normality. We've got 3 ways to get normality in chapter 10 and in chapter 11. 3 ways. Number 1, are the sample sizes bigger than 30? Okay, which that's the case here, so that's nice. Okay, number 2, or does it say things very approximately normally up here? And if that's not true, you graph the data, and as long as you don't have outliers or strong skewness, you're going to say normality is met or normality is reasonable. In this case, we really like it when we have big sample sizes, because all you got to say is this. You say one sample size is 50, the other sample size is 45. They're both greater than or equal to 30. You have to clearly say that they're both greater than or equal to 30. So by the CLT, the central limit theorem, normality is met. In other words, the sampling distribution is approximately normal. Just as in previous tests, there'll be multiple choice problems asking you about these things. It'll be, what fact allows you to use the formula for the standard error? And you'd say, oh, the population sizes have to be at least 500 and 450. Okay, that would be the correct answer. Okay, or it could be ask you what establishes normality in this problem, or what guarantees you have normality in your sampling distribution. Oh, that both your sample sizes are bigger than 30. So make sure you're cool with that. We've had that for a few chapters now. All right, so we've got the type of inference, the hypotheses, the assumptions, now the mechanics. So the mechanics, we need our test statistic p-value. And since it's t, we have to have the degrees of freedom, okay, which you can get all that of your calculator. So this is what we'll do. Let me show, I'm going to go ahead and show you the shortcut with your calculator, all right, because you can always use that. And so here we go. So what we'll do to get our test statistic p-value, we go stat, we go tests, and it's option 4. Option 4. So this chapter is all about option 2 and option 4, a 2-sample t-test. So we hit enter on that. Now, in this case, we aren't given the data. We aren't given lists of numbers. We're given the stats. So we hit enter on stats. And so, okay, our first X bar is for the females at 78.2. So I'll hit 78.2. Our first standard deviation, that S sub X1, that's our first standard deviation. And so that's 5.2, right like that. And then our first sample size is 50. And then for the males, the mean is 74.6. So I go 74.6. Very nice. And that's 8.2 is the male standard deviation. I like that. And so then we get 45. Our alternative is not equal to. We always say no to pooled whenever our calculator asks us whether or not we want to pool. And so we go calculate. And so there it is. There's our t-test statistic. There's our p-value. There's our degrees of freedom. And those are the numbers that you have to write down, which I have written down right there. Okay. So you don't have to show your work on this. You have to, I'm going to talk about this in a second. You have to be able to recognize this formula. Okay. But the 3 things you have to write down is your degrees of freedom, which you can get off your calculator. If you don't have a calculator, you can just estimate, you can just use the smaller sample size minus 1, which would be 44. So on this one, a correct answer for degrees of freedom would be 73.02 approximately, or 44. Either one of them, they create slightly different answers, but they would work, okay? There's your t-test statistic, okay? That, of course, is right there, and there's your p-value, and right p-value, a very small p-value here. All right, so that's a small p-value, okay? And so then before I talk about this formula, let's talk about our ending, our conclusion with our p-value is, are we going to reject or fail to reject the null? And do we have convincing evidence for the alternative based on the p-value? So you would say this p-value is less than our alpha of 0.05. We were not given an alpha, so we use 0.05. So make sure to be careful about that. All right. So this p-value is less than 0.05. So I reject the null hypothesis. There is convincing evidence that, and you restate the alternative in context. And you can state it like this for me. Technically, you're supposed to rewrite the context, but that's sort of a lot to me. So if you just write it like this, then that is that to me is full credit, and it should give you full credit on the AP exam. Although I would go ahead and write it all out because it does sort of irritate some of the gurus. So if your p-value is low, reject the null, and you have convincing evidence, and then for the alternative. Okay. If your p-value is greater than 0.05, you do not reject the null. You do not have convincing evidence that, and you restate the alternative again. So we've done that for a couple chapters now. Now let's talk about how to find that t-test statistic. All right, so if you didn't have a calculator, or if you're asked to do this, okay, you're asked to find the formula for a test statistic. Remember, every test statistic on your formula sheet is statistic minus parameter over the standard error. Statistic minus parameter over standard error. Okay, well, our statistic here, we got two of them. So, and it's the difference in two. So our statistic is 78.2 and 74.2. Okay, so what's our parameter? Well, we got two of them, and that's mu sub f and mu sub m. Okay, but they are, if we use the reasoning that the null hypothesis, we're assuming the null hypothesis is true as we do this test, mu sub f is mu sub m. If we assume they're the same thing, then their difference is zero. So in other words, our parameter is in essence zero here. Standard error. There's the standard error. Where do we get that? So on your formula sheet, there's your formulas for standard error. That's for section 1. That's for section 2. Right there. So the square root of that over that. Of course, you could do one variable stats and find these numbers, but the easiest thing to do is just to do that 2-sample t-test and get there's your S's right there. Of course, you can scroll down and you already know your N's. And then plug them in, and then you get 2.52358. Okay, and so that is your test statistic. It is used to find your p-value. Now, how would you use your test statistic to find a p-value? And you need to understand how to do this. Well, what our test statistic is telling us. See, this is our t distribution with this problem, and our degrees of freedom is like 73.02 approximately. Every t distribution is centered at 0. Okay. And so our t-test statistic, which is telling us how different our sample values are, is somewhere over here. Okay, somewhere over here. So about 2.52358. Our p-value is the area on the outside of this, okay? Because this is a not equal to. If this had been greater than, we go greater than. If this had been less than, we go less than. But if it's not equal to, it means we go outside of this, and we go, since it's two-sided, not just that big or bigger, but it's either way. So the not equal to is both greater than and less than. So negative 2.52358. And so how do we find this area? Do TCDF. So we'll do TCDF. So we'll go second vars, which is distribution, and go TCDF. CDF functions tell us p-values. And so we are going from 2.52358 to infinity. So just at like 9 billion or something. And our degrees of freedom is like 73.02, like that. And so we go like that. And so that is that area. So this area is 0.06896, but it's got two parts to it. So if we multiply that times 2, and so that's our p-value. And so that is how you find the p-value by hand. Having said that, you can always use that 2-sample t-test functions. Okay, the next thing is this. Be able to make the connection between the interval and the p-value and your hypothesized value. Create a 95% confidence interval with the data in context 1. Make the connection between the interval, the p-value, and the null hypothesis value. Okay, so this is what we do. Just like last chapter, let's make our interval. So you remember we go stat, we go test, and we would go down to option 0, the 2-sample t interval. So we hit enter, and notice it went ahead and entered all the numbers for me because it knew I was fixing to make this point, and it asked for 95% confidence. So I go 0.95, no to pooled, and hit calculate, and there's my interval. Okay, there it is. So what's interesting about that interval in this case, 0 is not in the interval, which means it's not a plausible value, and so be rejected. So we did a very similar thing like this a couple of chapters ago. All right, so there's our 95% confidence interval. And so remember, our null hypothesis is that the difference is 0, okay? But 0 is not in the interval, so it is not a plausible value for the true difference and should be rejected at 95% confidence, okay? The low p-value below 0.05 also tells us to reject the null. So if the 0 is not in the interval, it's to be rejected, and you're expecting a low p-value. How low? Below the related alpha value. So, and the related alpha value with 95% confidence is 0.05. If this had been 97% confidence, then the alpha would be 0.03. Okay. And this only works for a two-sided test. Okay. For a two-sided test. Okay. If it was a one-sided test, it actually works. You got to divide your alpha in half, but we aren't worrying about that right now. Okay. So that is, okay. So that's the main kind of problem in the chapter. Let's look at the type of problem when you're actually given, the data. You're actually given the data. So the other kind of thing that can happen to you is when they give you the data like this. They give you the list of numbers. And so let's see if we can handle this one. So this says a company owns two factories, one in Athens and one in Decatur. An executive of the company wishes to see if there's a difference in the mean. So we know it's there, there's going to be a difference in means. So this means it's going to be a T procedure, and difference, it means it's going to be a two-sample T procedure probably. All right, so in the mean number of errors committed by the workers at the two factories, he takes a simple random sample of 9 workers at each of the two factories and notes the number of errors committed by the workers over the course of a week. Shown below, do the data provide evidence of a difference in the means of the population? Perform hypothesis test. So certainly their numbers of errors are different, but are they way different? Are they statistically significantly different to where they would make us to believe our population values are different? All right, so it says perform a hypothesis test. We have to do the FAME acronym. We got to say what we're doing. There's our name, two-sample T-test for the difference in means. Our hypotheses are going to be that there's no difference. That's always in this section going to be your null hypothesis. There's no difference, or that the difference is 0. Nowhere up here does it hint that it says we feel that Athens is more than Decatur, Decatur is more than Athens. So we go with not equal to, the two-sided test, and we define our parameters here. Mu sub A is the mean number of errors committed by the workers at the Athens factory in a week, and mu sub D is for those for Decatur. Okay, so that's how you do your hypotheses right there. Then, just like what we just did, it says that SRSs were taken. So independent random conditions met. We're doing our assumptions, or otherwise known as our conditions. And so we ISIN independent random condition. There must be at least 90 workers at each of the factories for our sample sizes to be less than or equal to 10% of our population sizes. Okay, and so then now, normality. Are the sample sizes bigger than 30? No, darn it. Okay. And does it say anywhere up here things very normally? No. So what that means is we have to graph our sample data. And so you could make a histogram, you can make a box plot, you can make a stem and leaf plot, or you can make a dot plot. So when I'm doing it by hand, to me, it's just easy to do a dot plot. Just make number lines and put dots for each of those numbers, right, like that. And there's no outliers or strong skewness here. And so you graph the data. As long as you don't have any outliers or strong skewness, you're going to say normality is reasonable. And so this is what I said. The sample graphs show no outliers and no strong skewness, so normality is reasonable. There you go. So in other words, we feel confident that our sampling distribution is approximately normal. All right, and so now let's do our mechanics. Okay, so we got to get our degrees of freedom, our test statistic, and p-value, and we can use our calculator to do that. So let's do that. Okay, so we shall say stat. Well, first of all, since we're given the data, we've got to enter the data in lists. So you would go stat and then edit, and I've already entered the data. Okay, so I entered the data into lists. So now I've entered the data. Now I can go stat, and I can go test, and I go to two-sample T-test, right like that. So I hit enter. I entered the data, list 1 and list 2. And so the frequencies are 1. The alternative is not equal to. Always say no to pooled, and we go calculate. And so there we are. So there's our test statistic, p-value, degrees of freedom, and that's how you get it. So and so there you go. And so in a similar fashion, you could, if to use the formula like we talked about before, you could use these values to show the formula plugged in. Right there. So, or to find those values, you could do one variable stats, just like we did in chapter 1. And so you notice how big, that's a huge p-value, isn't it? And it's a really small T-test statistic. In other words, these things are not that different. Okay. The Athens and Decatur, and then you can sort of tell by looking at the graph, Decatur has more variability. okay? But their means are not significantly different, I would say, and that's what this is saying. Also, you have a really small sample size, right, for both of them, and so that tends to inflate your p-value. So you would say, this p-value is greater than 0.05, so I do not reject the null. There's not convincing evidence that, and then you restate the alternative. And like I said, on the exam, I encourage you to write all of it out again, that mu sub, and define mu sub A as the mean number of errors for all the workers at the Athens factory, and mu sub D for the Decatur factory. But this is okay. And so there you go. So a very high p-value. So if we made the interval here, we would expect 0 to be in the interval. All right, so that is that. Now, one other sort of problem in this chapter that's missed a lot. We had something really similar in the last chapter, okay? And that is when your data is paired. Okay, we're going to have to do a paired t-test. So let's look at this scenario. So this one said a new drug is thought to help senior citizens who are having problems with the memory loss. All right, 10 senior citizens who have been experiencing problems with memory loss volunteered to be part of a study to test the drug. Each of the 10 received the drug and were given a test that measured the quality of their memory from 0 to 100. At another time, each of the 10 were also given a placebo and then given the test. It was randomly decided. Looking for that word random. We always look for that word random, or SRS. Okay, it prevents bias. Okay, it was randomly decided whether each subject received the drug first or the placebo first. The scores on the test are shown below for each subject. Do the data provide evidence that the new drug works better than the placebo, the scores in the memory test? So are these scores in general with the drug, are they better? Are they higher than those without the drug? All right, the trick here, it may be tempting to do a two-sample t-test here, to do just what we did in context 2. You cannot do that. Why can't you do that? Because of this word. We don't have independence here. These are not independent samples. This is a paired sample. And remember, whenever you have paired data, what you're going to do is you're going to do a t-test, just a one sample t-test, with the differences. With the differences is what you'll do. So yeah, this data has been paired. This number goes with this one. This is the same person, okay? This number goes with this one, okay? And it's not independent because a score on one is associated with a different score on the other. If you make a high score on one, you're probably going to make a high score on the other one. Like this person made a high score with the drug, he made it without. But this person had a really low score on both. Okay, so if I told you someone made like a 90 something with the drug, you're going to say, well, they're probably going to make a 90 something without it as well. If I told you someone made a 30 something with the drug, they're probably going to make a 30 something without it in this case. So whenever data has been paired like this, you subtract the numbers and do a one sample t-test, just like in section 11.1 with the differences. So I just subtracted each of these numbers, that minus that, subtract them all, and then do a t-test. And this is what is known as a paired t-test. So, but it is in essence, we're treating as a one sample t-test. So here we go. And so I'll do a paired t-test for what is known as the true mean difference. The true mean difference, or you could say for the mean of the differences, okay? For all people like these, okay? So, of course, there's another little trick that you may have noticed here. These 10 senior citizens volunteered. Does that disturb you? It disturbs me because there could be something different about them that makes them different from other senior citizens. Maybe, okay? So guess who we can generalize about? Only people they have reason to believe that are like these 10, okay? The fact that they were randomly assigned means we could infer a cause and effect relationship. All right, so there's the name of our inferences, a paired t-test for the true mean differences, or a paired t-test for the mean of the differences. All right, so our null hypothesis is that the differences are 0, is that the null hypothesis, so our X bar is the mean of these numbers, okay? The null hypothesis is that for all differences, for all people like this, would be 0, okay? And mu sub D is the mean of the differences, drug minus no drug, of memory test scores. In essence, for all people like these, okay? I went with greater than here. Why did I go with greater than? Because it said, does it provide evidence the new drug works better? Well, if the new drug worked better, that means these numbers would be positive, okay? And so we went greater than there, Okay, so that's your T and your H, that's your type, and that's your hypotheses. Now your assumptions, okay? And we've had this happen a few times this year. We will sin, not I sin, because we're doing a one sample deal. It says it was randomly decided as to whether they got the drug or the placebo first. So the random conditions met. Don't say they were randomly selected. They were not randomly selected. They were, in essence, randomly assigned to take either the drug first or the placebo first, okay? So the proper way of wording that is this, is that the random condition is met for senior citizens like these. We always have to say like these when they were not randomly selected, or SRS. We do not have to check the independence one because we do not have, in other words, the condition of our sample size being less than or equal to 10% of our population size. We don't have to check that here because we don't have sampling here without replacement. Okay, so if you did, that'd be fine. If you said, hey, there's got to be at least 100 people like these, that would be okay, but you don't have to. All right, so then normality. Is our sample size bigger than 30? No. Does it say anywhere up there things very normally? No. So therefore, we graph all the differences. So I just made a dot plot here. The graph of the differences shows no outliers and no strong skewness. So normality is reasonable. Okay, so then we do our mechanics. And so let me do that for you right quick. So to do your mechanics, and so what you would do is we got to put our differences in a list. So I took all of these differences, all these numbers here, and I said stat and edit, and I put all those numbers in a list there. So there's all the numbers, okay? And so then we need our test statistic, p-value, degrees of freedom. Of course, the degrees of freedom is just going to be n-1, so it's just going to be 9 here. But anyway, so we will go just like we did in section 11.1. We said stat, test, and t-test. So we hit enter. This case, we have data. It's in list 1. And our null hypothesis value is 0. So list 1, frequency is 1. Our alternative is greater than. And so we go calculate. And there's our test statistic and p-value. And of course, our degrees of freedom is sample size minus 1. So it's 9. And so there is that. So those 3 numbers there, boom, 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 okay? And that p-value is above 0.05. If the p-value is low, you reject the null. Otherwise, you do not reject it. This p-value is greater than 0.05. So I failed to reject the null. There is not convincing evidence that, and then you restate the alternative. There's not convincing evidence that the mean of the differences is greater than 0. In other words, we can't say definitively that the drug works. Okay, that's a run through of chapter 11, section 2. I encourage you to, to do the assignment and to think about this stuff and to ask me questions that you have. And I hope you have a good experience with you. And thanks for watching the video.